I'm Maciek. I'm from Rzeszów, and I'm here to talk about something we haven't talked at this conference. Because at this conference, we are talking about writing good software and about writing features, right? And that's probably about 80% of our work. And I am here to talk about the other 80%. I am here to talk about the bugs. And specifically about the bugs that are harder than other ones. You know, the bugs that can't let us, that stay us awake at night. Have you ever been there? You've been checking your program, your application, to fix something, and you've checked every single line twice, and you've changed every single line twice, and it still doesn't work. Or have you been there? You're getting a report about a failure on production, a user is really, really angry, and all you can say is, can't reproduce, can't fix. Or have you been there? You've been debugging something as a team, probably the same bug, because it arrived for the third time, and you still don't know how to fix it, and there is this guy coming, a hero, saying, I know! And he disappears for 2 days, and then he comes back with 2,000 lines changed, and you deploy to production with high hopes, and it doesn't work. Or have you been there? You see a bug incoming, you think, it's not ours, it's theirs. You reassign, only to see the same bug circling back to you after a week and 3 teams bouncing it off. Or have you been there? After all those things happened, your manager comes asking, what have you been doing this week? Debugging. Oh, that's great. How many bugs have you fixed? None. Oh, so what's the progress? I don't know. And on the top of this, when you are in this debugging spree in a team, it often happens that you fix the same bug, that you fix the same line. With your colleague, there are conflicts, people start venting off, people start finding a scapegoat, right? This is harsh. I shouldn't ask if you've been there. I should ask you how many times you have been there, right? Because that's our daily life. That's the other 80% of our work. I have been there many times. And you know, I must confess, but don't tell anybody. Sometimes I question my life choices. Sometimes when I see bugs like those, I think that working remotely is okay for me as long as it means working from a remote part of Polish mountains as a shepherd, not as a software developer from my home office. Have you been there? And if I stand here, it means that I'm not a shepherd, right? I don't look like a shepherd. I'm not the guy in Texas hat. If I stand here, it's because I have found a very effective way of dealing with bugs. I have found a very effective way of going through the process of not knowing the answer, of knowing who should fix it, how it should be fixed, and how to report the progress, and how to scale it to the whole team. And I found hope, and I'm here to share it, because I realized that many of my peers use the same method. That's not that I invented this, I just stumbled upon this. And that's the method. I use it in my daily work at Chattermill. It is a small company, but the system is quite complex because we ingest data from customer reviews, we have terabytes of textual data, and then we need to push it through some ML models. So the backend team, I'm a backend developer at Chattermill, the backend team orchestrates the dozens of machine learning services, so it is pretty complex. And sometimes, just sometimes, it happens that we also have a bug. And I use this process, and it is very effective. So yeah, I am here to tell you, after 10 years, over 10 years of my experience, do not despair. Do not look for junior shepherd jobs when you see a bug. Just debug like a scientist. You may ask, no, not a shepherd, but a scientist? That's weird, right? What do the scientists know about bugs? What do they know? What do scientists do? They invent weird theories. They spend our money on expensive experiments, and they write papers nobody reads, right? So what do they know about the bugs? We are a practical bunch. We know about bugs. What do they know? So I would say that a bug is a surprising way reality behaves. It should work. We understand why it should work, but it doesn't. It's a surprise. And that's what also happens in science. Well, let me tell you a short story about a small crisis that physics faced in the end of the 19th century. In the 19th century, physicists thought they knew almost everything about the nature of light. They indeed knew a lot. They knew that a light is both a particle and a wave, and they were able to measure the speed of light, which is quite impressive. But they believed that this wave, light, should be requires a medium to move, just like sound requires a medium, right? So they coined a theory that there is a luminescence ether, and the Earth moves through this ether, and that's how light is transferred through the outer space. And they wanted to measure the speed between Earth and this ether. So Michelson and Morley in 1887 proposed designed an experiment when they sent two orthogonal rays of light, and they wanted to measure the difference of the speed between those lights, because one of those rays goes with the Earth, one is orthogonal, so there should be a difference, and there was none. So they repeated, and there was no difference. It was a surprising behavior of the reality. It was a bug in the physical theory. So what they did is what we do. They tried to patch it. They proposed some ad hoc hypothesis, but nothing worked until a young clerk from a Bern patent office came, and instead of yelling at the reality, he decided to describe it. And to describe it, he started with two basic observations: that the physical laws should be the same in every frame of reference, and that the speed of light is constant, no matter if an object is moving or not. And Einstein, starting from those two premises, provided some predictions, provided some formulas, and published it as a paper. And people were rather hesitant at first to accept it, but then this paper happened to explain the reality very well, and also it was confirmed by experiments. And this is what we now know as special relativity. And that's something that is taught at high school, so it's well-grounded theory now. It describes our reality, and it solves this surprising behavior known in computer science as a bug. What is important, though, in this story is not the result, it's the method that they used. So, at first, Einstein just guessed. Einstein proposed a hypothesis. Okay, I believe this happens. And then he calculated predictions based on this theory. And based on those predictions, other physicists were able to test the theory, to design experiments to verify it or reject it. And that's what Feynman said is the key to science, because if the theory is nice, but the experiment rejects this, then we reject the theory. But if the experiment confirms the theory, we say, yeah, for now we say it's true. And that's something that I believe we could use for debugging. And if you don't see the clear connection yet, let me tell you 3 stories of debugging 3 very nasty incidents. First one, we faced issues in integration tests. Do you do integration testing? Do you like it? No. Who likes poor integration tests? It was, for me, it was a sizable company because it was hundreds of developers, dozens of teams working on the same product, on the same repo. And it happened that we had issues, we had errors on integration tests in this repo, and it meant that all the teams were blocked or almost blocked because the issue is intermittent. And the issue was raised by a library that my team added. We were working on optimizing an API, and we needed this library to optimize it, and we needed it badly to reach our deadlines. And because this error was raised from our library, from the library we added, we had a virtual mob in front of our virtual doors. We were working remotely, yelling, remove the library, remove the library. Yeah, they had virtual pitchforks in their hands. And we didn't want to do this. So instead of jumping to the conclusion, this is the library to blame, we started digging. And first, I wanted to gather some context to understand how this library works, so I started reading the source code. It is Ruby, and we Rubyists believe that Ruby is read like English. My peers that don't do Ruby says it's not, but bear with me. I'll be explaining the code well enough. So I have found the place where the issue is raised. And yeah, that's a valid place to raise an error. The problem was that we had a guard statement and the configuration param, and we had no chance to reach this place because we should have returned earlier. That was surprising. So I was checking our application code. I tried to observe how it works, and I realized that we indeed changed this configuration param, but then we changed it back because it's in before and after hook in a request. I thought, that's weird. We shouldn't reach this place of the code, but it looks familiar. It looks like a race condition. Would it be a race condition? It was just a wild guess. I published it on our War Room channel. The stake was quite high because I was promised PhD if I were right. I still haven't got my diploma. And so yeah, it was a wild guess. It is a race condition. Or rather, it wasn't a guess because we are software engineers, right? We don't guess. I proposed a hypothesis, and then I designed an experiment to verify it. Yeah, I prepared the simplest possible experiment. It wasn't even multi-threaded. I just simulated the threads, two threads in the same script. The first thread, the business one, was setting the configuration value. Then it was running some business code, this finding the data in the database, and then loading related data. And then I interleaved it with this before hook code that was changing the param. And I ran it, and bam, I failed successfully. I confirmed that it is possible to raise this issue if the threads interleave in this manner. It's quite possible. So we had strong evidence that it is the before filter that wasn't thread safe. We were changing not a constant that wasn't a thread safe, that wasn't really a real constant. That was the cause of the issue. And we had a very good reason to go to the team that introduced this before hook and ask them politely, you know, folks, it is this change that causes the issue that blocks the whole company. You know, no hard feelings, but we are reverting it. And with this strong evidence, it was possible because it wasn't blame casting. It was solving the problem. And what happened here? We started by gathering information from all places possible, from the source code of the library, from our source code, from the behavior of the application. Then we basically guessed what is the solution, what is the potential issue, and then we verified this guess with a very, very simple experiment, very cheap experiment. And it led us to understanding, and this understanding allowed us to fix the issue. And this really resembles the scientific method, when we start with observation, then go through hypothesis, and then we experiment. And this is the foundation of this debugging process I want to share with you. We act as a scientist with the scientific mindset. We don't start with the solutions for the problem that we have. We try to understand this problem well. And to understand this problem, we propose hypotheses. We guess what would be the explanation of this problem, and we try to prove or reject those hypotheses. And this is a very safe way of working, because you know, when you debug, this self-doubt is really related to the fact that you don't know, okay, I don't know why it doesn't work. I don't know how to fix it. And when you when you propose a hypothesis, you say, okay, I don't know, but maybe this is this one, but I might be wrong. No, not this one. Let's try another one. Oh, not this one. Let's try another one. It's the process when you say it's okay to be wrong until you're right. And that's something that's deeply rooted in the scientific approach. But it was a simple case, right? I was able to run the code locally. But what if something happens on a remote server and we can't reproduce it? Let's get back to our shiny integration testing suite that everybody loves. We had another issue with this, but this time not in the code, but in the infrastructure related to the integration tests. We had multiple services, and one of them was a GraphQL gateway. GraphQL gateway needed GraphQL schema, and the schema was pushed to the gateway container before the tests were run. And this pushing didn't work, and we didn't know why. We weren't able to connect to GraphQL gateway, and that was surprising, and that was harsh because it looked like a black box. You know, I'm a developer, and in the team we had developers and QA engineers, so our first reflex was, oh, this is infra. This is a black box, we don't know. But then it was a blocking issue, we had to fix it, so I started digging. And I checked, just as in the previous case, okay, this line of code raises an error. We send a post, maybe this post is too big, and that's why we can't, there is a timeout while connecting to this external, to this container. So maybe instead of sending a post, we can send something very, very small, like head request, HTTP head, to check if we can connect with head. I was very wrong about the nature of the error. I was very wrong about trying to send a head where a post is sent. But yeah, I did it. I was a bit in despair because I was debugging. And what happened? Oh, I saw another error, different one. This time it was a read timeout. I thought, yeah, read timeout. There was, cannot connect. It's different. What's the difference? What's this read timeout? Why just not a normal timeout? I started reading and I learned that read timeout is special. It's different than open timeout, because when you get a read timeout, it means that the remote process probably works and the port is open on the remote server, but it doesn't respond to your TCP connect to your TCP communication. So I thought, okay, so it means that the container starts, but it doesn't respond. That's interesting. Why could it happen? So I started reading more, and because we were using Docker Compose to orchestrate the containers, I was checking their GitHub issues, and I found that indeed, in some cases, there is a bug in old Docker Compose that we happened to use, that container can freeze if it logs excessively, because the logs are not drained. And I checked that we log excessively from the health check endpoint. There were a lot of dots, so I thought, yeah, so maybe this is this bug in Docker Compose. The easiest way of fixing it would be to update Docker Compose, but updating it on our test infra wasn't a simple task. And I didn't have enough data to go to the infra team to fix it. So I wanted something simpler. I wanted a simpler experiment to verify my hypothesis that it's because of those Docker Compose bug. I just removed the logging from the health check endpoint, and I pushed it, and it worked. And it worked all the time. So this way, I verified that it is a Docker Compose issue. It gave us the understanding. And with this understanding, we are able to go to our CI infra team and say, OK, at your convenience, please upgrade Docker Compose. It would help us greatly. And yeah, they did, but the bug was patched before. And what I learned here were two things. The first thing is that, during the debugging process, you're often in the dark, and you don't know what's relevant or not. And at this moment, for me, it works great to behave like a scientist in a lab. Whatever I observe, I write it down. Whatever I see, I write it down. Whatever is surprising, I write it down. Whatever questions I have, I write them down. And I don't have fancy software for this. I was using just Markdown in VS Code. Right now I use something more advanced like Obsidian, but still, it is plain text / Markdown, and I copy-paste everything there. Stack traces, logs, then parts of those logs that feels to be relevant, and most of all the questions that I have in my head, because they lead me, they guide me through the process. And also, there are two ends of spectrum in software development. There are people who prefer to spend a week in a lab, in a workshop, in order to save a day in a library, and people that are in the reverse, that want to spend a month in a library instead of writing a line of code. Don't be either of them. The balance between active experimentation and trying to understand how the stuff works inside and trying to build a mental model should go hand in hand, and that's how the debugging process is pushed forward. Next thing, the last one. The previous ones were interesting but small. This one was huge. This bug was embarrassing. This bug was preposterous. Because our production servers were responding with 502 errors every 30 minutes. Like an express train. Every 30 minutes, we were getting production issues. And our business were coming to us asking, OK, we have issues on production, right? Yeah, that's right. Why do we have them? We don't know. So where could it be fixed? We don't know. That was really embarrassing. So a sizable task force was gathered trying to fix it. We had a lot of hypotheses. I joined late, but we had a lot of hypotheses why it didn't work, and we started to verify them. Maybe we have a cron job running every 30 minutes, and maybe this is because of this cron job. Or maybe we have a memory leak, and we accumulate wasted memory until it breaks. Or maybe we just did DDoS ourselves because some other service has a cron job. Maybe we have a recent change in our code base that did this. You can see we had a lot of hypotheses, and I noted that was the moment when I noticed that my colleagues that I highly estimated, that my colleagues used the same process. They were proposing hypotheses, they were verifying them. We were self-organizing to split in small teams to verify those hypotheses, to check them. And it was effective in a way that we were pruning the options and that we had more and more observations about what could happen, what could have happened. What we noticed early is that the 502s are correlated with build-ups in our observer queue, in our observer request queue. The observer was called passenger, and also that they coincided with passenger restarts. So we started digging even more, and we noticed that the issue happens only on a one node at a time. We had several servers, and only one server was failing, different one every time. So it got us thinking, it must be some local state buildup. Maybe it's a state of on a file system. Maybe it's a misconfig on the web proxy that redirects staff requests to a single server. Maybe it's something wrong with the Debug proxy that builds the state for one connection. Or maybe it's a memory leak, because yeah, that's a local state buildup, right? I was certain it was a memory leak. And I felt it's not a hypothesis. It's just something I need a proof to show it, and I'll be the hero who saved the company. So it kept me up at night. Really, I put my kids to sleep, and I got back to my computer intending to do something else, and I thought, I need to check something with this bug. Please don't ever do this. Work is work, home is home. Don't mix it up. I did, unfortunately. I wanted to correlate data from various sources. So I started with the stats about the length of the request queue, and I noticed that it started at 1020, and then 4 minutes later it saturated, and then 3 minutes later the number of requests dropped and everything was back to normal. Then I correlated it with logs and with memory stats, and I noticed that the first client timeout was before the build-up, not during the build-up. That was curious. I also noticed that we have a memory peak after the build-up is resolved, when everything is normal. That was interesting as well. And I also noticed that after this memory peak and after the restart, we have high number of processes in our observer, and then this number of active processes is decreasing until we reach the point of the request buildup. I didn't understand any of this. I had just had some observations. It was late at night, so I thought, yeah, I'm done with this. Let's just wrap it up. I wrote a short note on Slack with my observations, with my hypothesis, with my questions, with my ideas. And I went to bed. When I woke up, I got answers, because we had people in Argentina, in Brazil, and when I went to bed, somebody was working and somebody used my partial results. And my Argentinian colleague explained that, yeah, so we use passenger, and passenger has this feature that when there is an error during startup, it blocks spawning new processes. It's called passenger resist mode. And indeed, we have an error during startup. There is the passenger start timeout, and it means that the application takes too long to boot up. And yeah, that was an interesting observation, and that was helpful. And we thought, why could it take so long to boot an app? The timeout was about 30 seconds, and we locally, the app was booting quickly, and in production it should have been even faster, because on production we were using a library called Bootsnap, and this great Bootsnap library was caching some startup information to make sure that the process on production starts faster. And so we checked this Bootsnap cached, and we realized that it's too big. It was 16 gigs. And reading those 16 gigabytes of the startup code, the startup cache, took more than 30 seconds, and that's why we saw the passenger timeouts. So we did the simplest experiment possible. We removed the cache, and we didn't hold our breath this time. We were checking other options, of course, because we weren't sure it was an intermittent issue. But after half a day, the issue didn't reappear, and we realized that, yeah, we have the solution. On a side note, the issue happened because we upgraded Bootsnap, we upgraded this library, and we forgot to upgrade the deployment scripts to properly invalidate the cache. And we upgraded this library half a year before. So we had no chance to check our GitHub changes and correlate them with this production issue. And over this half a year, the cache was slowly building up until the moment when it started to raise errors. I learned a very important lesson here. I learned how to scale the debugging process. We were gathered from multiple teams. I don't remember how big was the working group, the task force, but I would say it was around 20 people. And we were able to collaborate effectively without central coordination because we were following multiple paths of inquiry. People were proposing hypotheses, they were teaming up to verify them, and that's why, and because we were very open about this, we weren't stepping on each other's toes. We were also able to collaborate effectively because everything was public. We were sharing partial results. There was no hero attitude, okay, I'll fix it by my own in 2 days and then I'll be a hero. We were just publishing partial results, and it was available to everybody. And next thing, it allowed us to work around the clock, not because we were tied to our chairs and our keyboards, but because we had people spread globally, and when we published our partial results in Europe, our colleagues across the pond were able to pick up where we left off and continue debugging, and then leave their partial results, and we were able to stand on the shoulders of the giants, right? And next thing, this hypothesis-based approach, this hypothesis-driven debugging, allowed us to radiate the progress. It's not that we knew we are 80% there to fix the bug, but we were able to say, we have verified those hypotheses, we had all those left, and we are working towards this. That's how we were able to tell the business what we are doing and that we are really working. And also, this approach based on hypothesis hypothesis is a very effective way to coach your junior teammates and to scale yourself, especially as a senior developer or staff developer. Because instead of fixing something for them, you can fix something with them. When you realize that your junior teammate has a bug to fix and he's stuck, you have a set of questions that you can ask him. Okay, so what do you observe? What is the surprising behavior of the application? Okay, this one. What do you think? If you were to guess, why does it behave like this? Okay, that's a nice hypothesis. Now, could we verify it somehow? Yeah, that's a good idea. How long would it take? 2 days. Oh. Or maybe you can propose something to test it in 2 hours. Something very dirty, but 2 hours. Yeah, let's try it. Okay, you rejected this hypothesis. We have some progress. We know that it's not this. What's your next hypothesis? And that's how, instead of coming there and becoming their hero, you can make them a hero of this debugging process. And that's the next step in this scientific debugging approach. You know, when you're a scientist, you either publish or you disappear as a scientist. And in ideal world, the scientist progress. That's a scientist proposes a theory that someone else proposes how to verify it with an experiment, and somebody else reproduces this experiment, and then step by step in this asynchronous and decentralized manner, the science progresses. And that's how we can also move forward our debugging processes when we publish our partial results and when we are open about what we do. We are able to work in a decentralized and asynchronous manner. And also, what is required here, if there is any manager in this room, it is also what should happen in science, is that you are rewarded for the impact, not for the sheer volume of the papers you produced. So in science, if you are a good scientist, people quote you and people build upon your work. And in debugging, if you watch a group that debugs, you should look for the results that are seminal, that help other people to progress, because there will be people generating noise, but there will be people that push the process forward, even though they are not the one that finally fixed the issue. As I said it's a great way to coach your peers and to scale yourself as a senior developer, and also it is the way to radiate the progress and to show the stakeholders, the sponsors, the wider organization that yes, we have the issue, but we are actively working on this issue. And we have started with this desperation, right? With questioning our life choices, with planning to be a junior shepherd in Bieszczady in southeastern Poland, and I promised you to show you the way out. And the way out is in science, but it is not in scientific results. It is in the scientific working process that we can get inspired by, and again, that we can borrow from the scientist, and that we can use to answer our hard debugging questions, how to progress the debugging by the right mindset, understanding, looking for understanding, not jumping to the solutions, by proposing hypotheses, by being bold to guess what the issue is, and then test this guess and reject it boldly, by having the set of habits like a scientist in a lab, by writing down everything, by balancing active and passive learning, and then we are able to scale the debugging process. We know, because we will know how to collaborate with our peers by publishing partial results, by coaching other people, and we are also able to show that we are not wasting time and money because we show the report. But you know, there is one part missing to finish the whole process. When you debug, you start with a surprising behavior of the reality, and then you work hard to understand why it happened. And you should make sure that this understanding stays with you, that is persisted. And the best way to make sure that that the knowledge sticks is by conveying it to someone else, by explaining it to someone else. So whenever you finish fixing one of those harsh bugs, share what you learned. Write a postmortem, prepare a meeting inside the company, write a short Slack note. We had this issue that were the hypothesis. That's how we fixed it. Tell it to your friend or to your colleague over a glass of juice, or come to a meetup or a conference and share your story, not only to help others, but also, and maybe foremost, to help yourself to retain this knowledge. And you know, that's how, it's also how the scientific world works, because have you noticed that we ask the PhD candidates to teach their younger peers, to teach the undergraduates, and we do it not only because of the shortage of staff in the academia. We also want the PhD candidates to learn deeply their field and to understand the basics very, very well. And the best way to understand the basics is to explain it to someone else. So if you want to retain the knowledge that you acquired during debugging, please share it. And instead of going to be a study and becoming a shepherd your bugs in order to remove them from your code base. And that's it. If you have any questions, there is no mic here, so I'll be here and I'll be happy to answer them. And I'll be also around during the conference. I'm very, very happy to talk about debugging. Approach me freely. Thank you.